Hey everybody. Um, Today we're going to begin a 3-lecture study of parallelism. Uh, some of this material can be conceptually challenging, but it's also a lot of fun. So it's one of these things that is interesting because it's interesting both theoretically and practically. But before we begin that, I want to take a little poll. So this is a uh, Slack poll. So get your Slack thing ready, and uh, and in the poll, here's the situation: you and your partner discover a clever algorithm working on your project, or a compiler switch, or something that speeds up your code. Which of the following two things should you do, or would you do? A, keep it secret so that you can beat the other teams, or B, publish the idea on Piazza. Okay, so let me see. Okay, so right now the publish the idea on Piazza is winning, but it looks like the keep the idea secret is going, and the answer is not neither. Okay, so let's see. Okay, so this I wanted to clarify because it seemed like there was confusion. Everybody isn't on the same page for this. Okay, and let me encourage those of you who answered A to do B instead. Here's the course policy on information sharing outlined in the course information handout. So 1, you're not competing with other teams. The cutoffs for grades are determined independently of how teams perform. Okay? And 2, you'll receive participation points for sharing ideas and code snippets on Piazza. Okay, so 1 means that keeping it secret can't benefit your grade. And 2 means that if you do share, it will benefit your grade. It also makes it more likely that you can get a UROP with Professor Reagan Kelly or my research group. Okay. Now you've got to remember, you still can't copy code, but you can take inspiration from each other. Okay. And I hope that clarifies how we feel about this matter. All of us together form a big learning team. And you can help yourself by helping to advance the learning process for your peers. Let me just say that I also learned something about performance engineering every term from the students in the class based on the things they share. Okay. Yeah, cutoffs do not depend on other people's performance. Okay. And the standards are set, and then you are trying to meet those standards. Okay. So get some participation points. Okay. That's the point of this. This is not a cutthroat class. This is a class that we're trying to do team leading. Okay. Enough said about that. Let's go into the technical context. So let's recall the basics of Silk as Professor Reagan Kelly taught it last week. So here we have the fib function, and the Silk keyword, as you recall, preceding a function spawns the child function, allowing the parent to continue executing while the child task execute. Okay, the parent forks the child, and control goes to the very next statement after the spawn without the parent having to wait for the subroutine to return. Okay, then the Silk sync keyword joins the parallel tasks. Control cannot pass a silk sink until all spawn tasks have completed. That's why it's called fork-join parallelism. It could have been called spawn-sink parallelism, but the fork-join people got there first. Okay, and it's the most popular strategy for task parallel computing, whether you use Silk or OpenMP or TBB or anything else. Now, unlike something like pthread create, Silk keywords do not command parallel execution. Pthread create causes stuff to happen always. Instead, Silk keywords create logical parallelism, giving the compiler and runtime system the flexibility to schedule the tasks concurrently and hopefully efficiently. Now, Silk also provides loop parallelism with the keyword silk for, which is used in place of C's ordinary for keyword. Here's an example of using loop parallelism to transpose a matrix. The compiler converts this loop parallelism to fork-join parallelism using a divide and conquer algorithm under the covers. And we'll go over that next time, because understanding how silk for is implemented can help you reason about parallel performance. Now, an important thing to know about C and C++, and this is not just Silk, this is ordinary C and C++, is that you can pass pointers to stack space down from parent to child, but you cannot pass them back up. Okay, so for example here, suppose that you have 5 functions where A calls B and C calls D and E. Now for a serial execution, B can see A's stack storage, okay, but A cannot see B's, because when A is executing, B either hasn't been called or it's been popped off the stack. D can see C and D's stack storage, okay. In a serial execution, however, B cannot see C's storage, okay, because C executes after B, and so C hasn't even been allocated when B executes. Now, symmetrically, C cannot see B's storage, but for a different reason. And the reason was it was popped off the stack when B completed. Okay, if C does try to sort of illegally look at B's storage, okay, looking at what's over, and it might be able to do that, the compiler and runtime considered that UB, undefined behavior. And one of the things about undefined behavior in C and C++ is that the compiler and runtime are free to do anything they want, including producing or executing bad code. So you don't want to produce UBs, which is easy to do in these languages. For example, by right shifting a negative integer. Okay, that'll give you a UB very quickly, and then the compiler can do whatever it wants. Okay, but back to stacks. So in Silk, it has what's called a cactus stack. And without going into how it works, which we will go into later, it supports C's rule. Okay, but it also allows multiple of these views to be maintained in parallel. So B and C, for example, could be executing in parallel if they, for example, were spawned off from A, and they can each see their own storage and see A's storage, but they can't see each other's. Okay, so we'll learn more about cactus stacks when we learn about the Silk runtime system. And that's pretty much what you have to know. Yeah, so the child only starts the line after the Silk spawn. That's correct. Okay, and in fact, if we go back, let me just go back one slide here to here. In fact, the arguments for fib of n-1, for example, the n-1 is calculated before the spawn. Okay, and then the silk spawn happens. And when that happens, now the computation of fib of n minus 1, with n minus 1 having already been computed, and now in the main in the main fib routine, the parent routine, it starts computing, evaluating n minus 2 and calling n minus and calling fib of n minus 2. Okay, so in this picture, the C in the diagram is not copied. Okay, it's shared. So if D and E are both looking at C and D makes a change to C, E will see that change. Okay, if they each have, for example, a pointer back to C's storage. Okay, they will both do it. It's not copied, it's absolutely shared. Okay, it's part of the reason that it turns out it makes it easy to think about the execution of silk compared to C and C++. Okay, the first topic I want to cover is the topic of races. And let me first just say that one reason that parallel computing has taken a long time to gain a foothold is that concurrency introduces a new kind of bug that doesn't exist in serial code. And that kind of bug is a race bug. So race conditions are nasty, okay? They've caused enormous expense and even killed people. The Therac 25 radiation therapy machine, for example, was a medical instrument that killed 3 people and injured many more. The machine actually had, as I understand it, it had 2 power levels for its electron beam. For low power, a patient was exposed directly to the beam. But for high power, there was an intervening beam spreader plate that was supposed to scatter the radiation. So accidents occurred when the operator set up high power too quickly, and the beam spreader failed to rotate into place to block the high power beam due to a race condition. So zap, the patients got the direct high dosage, ouch. Okay, now previous models of the machine had hardware interlocks in place to prevent the illegal configuration. But the Therac 25 designers had removed them because they were expensive and decided to depend instead on software interlocks for safety. But they didn't get the concurrency right. So it was a bad idea. Okay? And then I'm sure you all remember the Northeast blackout of 2003, right? Well, I guess I remember it. So George Santayana said, "Those who cannot remember the past are condemned to repeat it." Okay, and this is one to remember, even if you have to learn it from history books or, sorry, I really am dating myself, from Wikipedia, okay, or I guess from a performance engineering class at MIT. So it turns out that a race condition existed in the Unix-based XA21 energy management system software produced by General Electric. This race caused data to become corrupted, producing an infinite loop in the code for the alarm system. And the bug then left operators with no way of seeing or hearing alarms that reported overloads in the electrical power grid. 256 plants went offline, and 50 million people were left without power, including me. Now, here's the thing about race conditions. They are notoriously hard to discover. You can test a program 1,000,000 times and never see the bug. And then one time, the stars align and bang, the bug shows up and wreaks havoc. If you're lucky, the bug will show up during regression testing and not in the field. But even then, you have a hard time getting the bug to repeat, so it can be next to impossible to find. Now, there are several different kinds of race bugs, and the one we're going to start with is the most basic one, called a determinacy race. You may have heard the term data race, which involves an atomicity failure. We'll talk about data races later in the term. Please don't use the term data race if you mean determinacy race. They're different. And one thing you'll discover about me is that I hate imprecise language about technically precise things. So don't make me angry. You wouldn't like me when I'm angry. Now, a determinacy race occurs when you have two logically parallel instructions that access the same memory location, and one of them changes that memory location. That can introduce non-determinism into what should be often deterministic code. Let's see how that works with a simple piece of silk code. So here we set the variable x to 0, and then we have a parallel loop with just two iterations, okay? And each iteration does something very simple. It just increments x. And after the loop, we assert that x equals 2. Now, if you execute the serial projection of this code, so remember the serial projection is when you replace, when you just drop the silk spawn and silk sync, and you replace the silk 4 with an ordinary 4, okay? So when you execute the serial projection, then indeed you always get x equals 2. If you run this serially, ignoring the silk 4, just pretending like it's ordinary 4, okay, it's going to increment, and then it's going to increment again, and it's going to be 2. Okay? But let's see what happens in parallel. Okay? Now we can visualize the execution as what's called a trace. So a trace is a directed acyclic graph, or DAG, whose vertices are sequences of executed instructions and whose edges indicate execution dependencies. Okay, well, I'll go through this in more detail and give you a more careful, a written definition, but I want to give you the idea first. Now, one thing you don't want to get confused between is a trace and a control flow graph in a compiler. A control flow graph in a compiler, a CFG, is a directed graph in the compiler's internal representation of the program, and it usually has cycles. In contrast, a trace represents dependencies between executed instructions at runtime, okay? And it's a DAG, okay? So let's see how this example works. So when we execute x equals 0, we end up with a node in the DAG that we're going to call a strand, that sets x equals 0. Okay. Then the silk 4 causes the trace to branch such that each of B and C on the left there, the two iterations of the parallel for loop, execute instructions. But those instructions, there's no dependency. One doesn't have to go before the other in the trace. But they both have to come after the setting of x equals 0. Okay? Now, at the end of the for loop, the two branches join, and the code asserts that x equals 2. Okay? So, now, it should come as no surprise, given your extensive familiarity at this point with x86-64, that x++ is not implemented as a single instruction. So let's look at a refinement of this graph that has the instructions really broken out much closer to what you would get in assembly language. Okay? And let's look at branch B, but branch C is similar. Okay? So the processing core reads the value of x into a register, okay, R1. This is in the left branch, okay? Then it increments the register, And finally, it stores the new value back into X. And then the two branches join, okay? And branch C does the same thing, but possibly in a different processing core with a different register. Okay, I called that register R2. Okay, so that's kind of what's going on. These are the dependencies. Now, here's the definition of a determinacy race again, and let's look carefully at how this definition plays out and what could go wrong. So first, I need two logically parallel instructions that access the same memory location. Do I have that? Yeah, the memory location is X. Okay, so what's the race here? So go to the Slack poll, and there's a multiple choice there giving you the opportunity to pick some possibilities. Okay. Yeah, you can take a minute to think. How many responses do we have here? We've got 70 people here, of which probably...
It says 33 total right now, or 30.
Yep, about 60 are in the class. Let's everybody just take a whack. If you can't figure it out, guess so that we can move on. And how many do we have here? I don't see, oh, there's the total votes, 42. Okay, now we're getting the others. Okay, good. Okay, so let's see how we did here. Oh, they don't give A, B, C, D. That's too bad because I want to refer to them by letter. Okay, so let's letter them A, B, C, D, E, F. Okay, so Helen and Tim, if for the future polls you can make sure that the letters are in there, that would be helpful. So let's see. If you answered B, C, or D, you're right. Those are all races. Okay. But first, let's step through the execution and see what can go wrong, and then we'll see why those are races and the others are not. Okay. So answer A is not correct because neither instruction is modifying X. Okay. But there are two types of races here, which we'll discuss in a moment. Okay, so A is not correct because you have to modify X. And in this case, they're both reading from X, and that's okay. Good. So here we have X and the two registers. And X is in memory, and the two registers are in the processors. Okay. Now we start out by setting X to be 0. Okay, and that happens before the fork. And now the execution has a choice which branch is executed next. So since the diagram is symmetric, let's suppose that the branch on the left is executed first. Okay, so we now execute R1 equals X, and so R1 gets the value 0. And now we increment R1, so it gets the value 1. And now suppose that this particular parallel execution starts next starts executing the right branch. Now there's a subtle point here, okay, which is actually very, very deep, deeper than you can imagine actually, if you haven't looked at memory models. We're treating the effect of the parallel execution as if it's interleaving the steps of the two branches. This assumption is called sequential consistency. And we'll talk about sequential consistency later in the course when we discuss memory models. By assuming sequential consistency, we can look at a parallel execution one step at a time as an interleaving of instructions rather than having to reason about several things happening at the same time. So there may be a choice, a non-deterministic choice, as to whether you're executing, in this case, one of two things. But it is a choice. You get to do one or the other. They don't really, you can view the execution as having done one and then the other, or the other and then the one. Okay. So let's go back to our example. Okay. So now R2 gets the value of 0, which is to say 0. Okay. It now increments R2 to get the value 1, and it stores that value back into X. And now the left branch does the same. It stores its value back into X. So now the assertion X equals 2 fails because the value of X is 1, not 2. Now I want you to notice something here. If we had executed the left branch completely before the left branch completely before the right branch, the value of X would correctly be 2. Or if we had executed the right branch completely before the left branch, the value of X would also be 2. It's only when we execute them interleaved, like that kind of, that the bug appears. Okay? If these two branches were embedded in a trace with billions or trillions of executed instructions, we might never see a situation where the race is triggered. Okay? What are the odds that they interleave just so? Pretty small. So you could test and test and test, and everything looks A-okay, and you run it in the field, and then one day, bam, okay? You get the bug triggered. Nasty, nasty, nasty. And actually, some people have argued that parallel programming is too hard because of race bugs. They claim that for a large code base, people can never get it right. One of the reasons we like Silk, however, is that Silk has a silver bullet to slay races. Okay, but I'm getting a little bit ahead of myself. Okay, now, for the people who answered A, this is important to understand. You could have, in this case, 1 and 2 and then 4 executed. And then it would be perfectly fine to, for example, do 3 and 7, okay, and then 5 and 6, and you would get the value 2. So it's not the reading of the value, it's the actual setting of the value, okay, that causes a problem to occur. Now, there are different types of races, and it's sometimes helpful to categorize them. Okay, there are 4 potential race situations with 2 parallel instructions A and B. If neither A nor B modifies a location, okay, there is no race if they both do reads. Okay, it's always okay for them to read the same location. Nobody's changing anything. Okay. The next 2 situations are symmetric. One instruction reads X and the other writes X. We call that a read race. Whether X is read before or after the write instruction might change what the reader sees, leading to non-determinacy, that is, different executions depending upon just what happens to happen. Okay? The last situation in the table is when A and B both write. In this case, one of the writes will be overwritten by the other, and so subsequent reading of that variable may get the value A wrote or the value B wrote, depends. Okay. So generally, you want to write code with no determinacy races. Determinacy races are almost always bugs in parallel programs. Occasionally, though, it may make sense to put in races intentionally. That's curious. So in Slack, what's the #1 reason people intentionally put races in their code? Okay, so this is free participation points. Randomness? No, not quite. Interesting. Interesting. Why would you intentionally put it in? Fast fail? No. Testing, execution, testing. Lottery? These are all good ideas, but they're not the #1 reason. What's the #1 reason? Okay. Yes, performance. Okay, good. Speed. Okay. Performance is why people do crazy things, which is why we have this class, so that you can learn how to do crazy things. Okay. But mostly, you want to avoid races and only program non-deterministically if you must. Okay, and we're going to cover non-deterministic programming, but much later. It's an advanced topic. Okay, so how do you avoid races? Because most of the time, you want to avoid them. So here are some tips. Okay, so first of all, the iterations of a Silk for loop should be independent. They should not be having the situation between the iterations where the two iterations access the same variable and one of them modifies it. Okay, that shouldn't happen. Okay. 2, so suppose you have a parent that spawns a child. Then the code of the child should not conflict with the code of the parent from the time the silk spawn occurs to the time the parent syncs with its children. It's fine if they both read the same variable, but it's not fine if one modifies the variable another needs to read. Okay. Now, it's helpful to know, as I mentioned earlier, that the arguments to a spawned child are evaluated before the child is spawned. So the evaluation of the arguments can't race with each other. Okay, you can't, when you're evaluating two arguments, they won't race. And they won't even race with the code after the spawn, because they occurred before. But OpenSilk allows you to spawn statements and statement lists. And if you do that and it contains a function, rather than spawning the function, the argument evaluations, although they won't race with each other, they may race with the parent because the spawn occurs before the arguments are evaluated. So that's the difference between saying x equals spawn of foo versus spawn x equals foo. Okay, that's the difference. Okay, so you have to worry about the races in those cases. Now, it turns out that when one or more fields of a data structure are packed into a single word, that can cause a race on some machines, okay? But fortunately not on x86-64. And the reason is that those offending machines do masking tricks to operate on subwords. They don't have hardware that operates on it and that worries about this, this particular issue. So what you think of as two fields, the compiler may actually pack into the same word. And then access to one field can cause a conflict with a modification to another field sharing the same word. Because basically it's doing masking and setting, it's doing bit tricks to affect it, and what it's really doing in the end is writing the whole word. But direct byte accessing is safe on x86, although you must still be careful if you're manipulating fields yourself with bit masks. Okay, so you have to be careful. If you're doing bit masks, then you are going to be writing full words. Okay. Yeah, so do we have to worry about races in function calls? Say you call a function from two children, would the function variables be over? And they could if they shared, global variables, for example. You very much could. But if it's going to be the stack storage, it won't share the stack storage. Okay, the stack storage is private to each of the instantiations. And okay, and that one's got an answer. Good. Okay. So moving right along. Okay. Now I mentioned that Silk had a silver bullet, and it's called Silk SAN, and it will find determinacy races. Okay. To use it, you specify the -f sanitize equals silk switch when you compile your code, which instruments your binary, and then you run the instrumented code. Now here's the promise. If your code has a determinacy race when run on a given input, Silk SAN guarantees to find it. If your code does not contain a determinacy race on that input, Silk SAN will certify it as that program run on that input as being race-free. Okay? Silk's algorithm has been proved mathematically. Okay? Other systems have what are called best effort race detectors. Okay? They may find some bugs, but it's not guaranteed. Silk SAN provides a guarantee, unless there's, sometimes sheepishly, we have a bug in Silk SAN or the compiler. Okay? But the algorithm provides a guarantee. Whether we implement it well is another question, and whether the compiler implements it well as well. Okay? Now, Silk SAN does not perform a static, which in this context means compile time analysis. It executes the code on the given input, and it keeps track of logical parallelism. The algorithm is quite clever, and the supplemental reading contains a paper that describes how it works. But it only tells you whether that particular input might cause a race. It doesn't tell you that your code is safe for all inputs. Okay? It only tells you. So you must still provide test inputs yourself to try to expose the bug. But if there's any way that the code could perform differently on that input than a serial execution would, Silk SAN will say so. Okay, it'll say you've got a bug. There's a different way of executing this that would generate different behaviors. Okay, but you must instrument your entire program. So Silk SAN's algorithm cannot help you if you fail to inspect all memory references in your code. So if you bring in a library from somewhere and you don't instrument that library, then you're going to be up the creek without a paddle if that code creates a race bug. Okay, if executing that code creates a race bug. Okay, so you want to ensure that all your program files are instrumented or you'll miss some bugs. Okay, so Silk SAN is your best friend for correct parallel programming. And I'll let you figure out why I put a greyhound on this page. Okay, here's an example of Silk SAN's execution. Okay, so here's an N-Queens code. It's not as efficient as the bit trick one, and it has a race bug, which I'll let you reason about on your own. It's using this. It's using an array to store the positions of the queen. Okay, and it turns out it has a race bug, and you can figure that out on your own. Let me just show you what Silk SAN gives you. Okay. So first thing is when you run it on a given input, the runtime overhead is nearly constant compared to a serial execution. There is overhead. It's about 7 times slower than if you just ran the normal code without a serial execution. And that turns out to be generally acceptable for debugging, although we're always looking ways to make it faster. And every now and then I get a UROP who is interested in, can they make it faster? Okay, we usually the the researchers in my group, the graduate students and postdocs and research scientists, it's one of these things of, yeah, we could make it faster. We've got so many other things to do. So we're always looking for people who might want to make it faster. Now, if silk sand finds a race, it reports it as shown here on the right. Okay. So, so you'll see on the left of this report, there's a little bit of ASCII art, okay, which shows the race context. And let me just explain what that is, because that'll give you a little bit better context, okay? So the first thing is that the lines that start with an asterisk, okay, those are the racing instructions. So for the first one here, it's a read and a write for the second, okay? And it gives the memory location of the variable being raced on and the file location of the memory accesses. So it tells you right in the file where that is. Okay. The pluses show the frames on the individual call stacks from the two racing instructions to the common calling context. So here we have, for example, a call on the left branch. We have a call and a spawn, okay? And on the right branch, we don't have any other things stacked up. And instead we have, and then the two calling contexts merge, okay? And at that point, this is where the cactus stack allows several parallel tasks to share the ancestry of their stacks while maintaining their own local frames, okay? And then the allocation context, it continues the further pluses that go down. So the stack here is growing up in the report, okay? I usually like to think of stacks growing down for calls, but the way we print this out is, it turns out we print it the other way around, where the root is at the bottom. I guess that's the appropriate thing for trees and cactus stacks. So the allocation stack is at the bottom, and it shows the context there where it's joined. So here are the things that are in the common calling context. There's a call and a spawn and a call, and then there's the allocation itself, which I didn't highlight, and then the stack going all the way back, very at the bottom, is main. Okay, and so it shows you basically how you got to each of these races. Okay, very, very helpful. And now you can take that information and figure out where is, what did I do that caused this race, and how am I going to fix it? Okay. Now here are some tips for effective performance engineering. Okay. Remember, we usually only care about performance if we already have correctness, okay? So here's the major tip, okay? And I've said it before. The trick to developing fast code is to maintain the invariant that your code is always correct. If you have well-structured code that is well-tested, it's much easier to engineer performance improvements, because if you accidentally introduce a bug, you find out right away when you test it, and it's easy to make changes. If you have poorly structured code that is poorly tested, you're unlikely to be able to make many changes at all that contribute to performance, okay? Because you'll end up doing 5 updates and then discovering you have a bug, and then you discover, oh my goodness, that bug has been there for a while. Where did we introduce it? And now you've got a much bigger set of code to look at. Okay, so this is one of my standard aphorisms. Okay, good code hygiene enables fast code. Keep your code clean, keep your code correct. Okay, and then you will get fast code. Okay. Good. Okay, I see that Jonathan is responding to Slack. So just let me know if there's something that I should deal with. Otherwise, I'm going to assume if you've replied, Jonathan, that that you have satisfied the student. Great. Okay, now I want to delve into the performance meat of the lecture, okay? Now, people bandy about the term parallelism without really knowing what that is, okay? They say this program is more parallel than that program. But if I ask them what they mean, they usually wave their hands and don't really have any idea how to quantify it. Still, they have no trouble talking about parallelism as if they do know how to quantify it. So today we're going to learn about parallelism so that if I ask you, you have a cogent answer, okay? So that you can quantify it and you know what it means to quantify parallelism, okay? Now I want to start with the Fibonacci program that Professor Reagan Kelly showed last time, where fib of n recursively spawns fib of n, and while that computation is executing, calls fib of n minus 2, and then syncs. Okay, so let's relate the execution of this code to a trace DAG like the one we saw in our discussion of races. But our trace will not only show dependencies, it will also show the function call activation frames. So here we go. Okay, we'll start out computing fib of 4. Now I've colorized the code so that all the instructions executed before the silk spawn are magenta, the ones after the spawn but before the silk sync are chartreuse, and the instructions after the sync are cerulean. Or in terms programmers can understand, pink, green, and blue. Okay. The key property of the color coding is that it's all serial code, which we call a strand. Okay, a strand is just a sequence of a chain of instructions with no embedded parallelism. But we'll also want to represent strands as nodes of the trace DAG. We will want to represent strands as the nodes of the trace DAG, okay? But we also want to represent the activation frames, which I'm showing as rounded rectangles here. Okay, now an activation frame, the thing that gets pushed onto the stack, usually contains a bunch of data, including local variables and the return address. But here I'm just going to illustrate with the parameter n that the frame was invoked with. In this case, for fib of 4, it's the value 4. Okay, and the circle in the middle there, the disk there, the magenta disk, is the strand that corresponds to the code on the left. Now, when fib of 4 is invoked, the code starts executing the magenta strand up till a silk spawn. Then it spawns fib of n minus 1, which is to say fib of 3 in this case. Okay? And that creates an activation frame with n equals 3. Okay? And now the new frame is ready to execute its magenta strand. But at the same time, the original frame can execute the continuation. Okay? So far, so good. But now what happens? Okay? Well, these two strands, the magenta one in fib of 3 and the chartreuse one in fib of 4 can operate in parallel. And they execute, and the fib of 3 frame now spawns fib of 2, while the fib of 4 frame also spawns, also in this case calls a fib of 2. Okay? So this is where the fib algorithm for me is painfully inefficient, okay? Especially because, I just hate to see work being repeated, okay? That's so totally inefficient. And it's repeated to the extent that it is doubly exponentially worse than the best algorithm you can do. But here we care about understanding how Silk operates, not how good the programmer was who wrote the fib code. Okay? So the fib 4 frame doesn't, in this case, go on to execute its next continuation, a cerulean strand, because it calls fib of 2 instead of spawning it. Okay? It calls it. And here I'm using dark shading of the frame if the frame is spawned and a light shading if it's called. Now fib of 4 must now wait for fib of 2 to finish, as well for the fib of 3 that it spawned off earlier. Both of them must return before fib of 4 can execute its cerulean strand. Now we have a bunch of new frames being spawned and more parallelism. Okay. So the trace DAG is unfolding dynamically, but the strands are embedded in the invocation tree. So the fib of 2 frames can now execute, for example, at this point, the 2 things they spawned off have finished, and they can execute their cerulean strands. Okay, so they do that. Okay, and now fib of 3 can finish up. And finally, fib of 4 can execute its cerulean strand, and the computation is done. Okay, so this trace unfolds dynamically. And the other thing to observe is that the code itself doesn't mention processors or any surrogates such as threads. It just exposes the logical parallelism among the tasks, and the Silk runtime system figures out how to execute the parallel tasks efficiently as the trace unfolds. Okay? So any questions there about about the model of parallel execution? Would it make a difference if fib of n-2 also had a silk spawn? It would be slightly less inefficient because you'd have the overhead of the extra of the silk spawn, which is a little bit more. A spawn is a little bit more expensive than an ordinary call, but it doesn't really affect things very much. Okay. Yeah. The overhead of spawning depends upon how you measure it, and we're going to talk about that later when we talk about the runtime system. But I think a rule of thumb here, so we've had Silk implementations that had it less than 3 times the cost of a call. Okay, I think now typically it is probably closer to, I don't know, I haven't actually measured it recently. I should know that. It's easy to figure out, basically. Run fib, okay, with spawning on one processor, and run fib without spawning on another processor, on one processor as well, okay, and compare the runtimes. That'll tell you, okay, because almost all that's going through in fib is function calls or function spawns, okay. Okay. But the overhead is reasonably modest because you're not typically spawning everything. Okay, the number of spawns tends to be way, way less than the other computation that you're doing. But not if, there are cases where it isn't, and then you have to know what's going on. Good, so let's standardize our technical terminology to make it easier for us all to talk about the trace DAG. So the trace is a DAG, and a node of the trace is called a strand, okay? It's a serial sequence of instructions without embedded parallel control. Now, what I've generally shown are maximal strands. In some cases, you could treat each individual instruction as a strand, but pictures are more compact if we coalesce as many instructions as possible into a strand. Okay, so that's why, a strand is something that, in some sense, you can define, but it can't have any embedded parallelism. Okay. Now, there are 4 kinds of edges: spawn, call, return, and continue. There's actually 2 kinds of return. There's return from a spawn and return time from a call. Okay. The spawn and call edges go downward in the picture. Return edges go up, and the continue edges are horizontal. And that's pretty much the way we, most of the time draw these things. Okay, they're all dependencies. Okay, you can't do one strand until you finished executing the previous one. Okay, the runtime system actually doesn't know about parallel loops. They're not represented directly in the trace. The compiler implements loops by transforming them to spawns and sinks. using a divide and conquer algorithm that we'll see next time. But conceptually, all you need is spawns and sinks to create the trace. And with recursive spawning, you can imagine if the fib parameter were much bigger, we would get loads of parallelism. Okay, in fact, we get a spectacular amount of parallelism out of fib. But that leads us back to our big question, okay? Exactly what is parallelism? Okay, so let's take a look at this trace, and let's assume for simplicity that each strand executes in unit time. What is the parallelism, okay, of this computation? Now, intuitively, parallelism is the maximum possible speed up of the computation, where speed up is the ratio of the serial running time to the parallel running time. How much faster is the parallel running time than the serial running time? And it makes sense that with more processors, a computation will generally run faster. But there are diminishing returns. As we grow the number of processors, at some point the extra hardware won't help us anymore. And for some finite number of processors, the computation runs as fast as it possibly can. What is that number of processors? Okay, that's what the parallelism is. Okay, when let's do another poll here. Okay. We'll come back to the fib one, but let's do a simpler problem first. Here's a simple DAG. It's not the fib DAG, and I've eliminated any invocation tree in which the strands would normally be embedded. Okay? What is the parallelism of this DAG? That is the maximum possible speed up. Okay? So for simplicity, let's assume that every strand executes in unit time. And let's please vote in the Slack channel. Okay? What's the parallel thing? So pick the closest number. Okay. So everybody should vote. Okay. If you're right, you're probably lucky, because I got this first when I tried to do it. Okay. When I first looked at this DAG. Hey, nobody's voting for, nobody's voting. I can't see which the, okay. Well, I don't want to see the top 4 choices. I want to see all the choices. Okay. So we got about 45 people. Okay. So E5 leads, followed by 2, followed by 3, followed by 4. Yeah, it's like that. We have a lot of different answers. That's pretty much the state of the world. Okay. People eyeball the parallelism. Okay. We're going to find out the answer after a little bit of analysis. Okay. So the study of parallelism goes way back. Okay. I feel like I'm giving a history lesson here, but I guess I've qualified. Gene Amdahl was the chief architect of the IBM 360, System 360, which was the dominant computer of its era, which was the 1960s, and also the 1970s, except they renamed it to the 370. Now I'm paraphrasing what Amdahl said, okay, here. And in fact, when I read his paper, I was hard-pressed to extract any words that say what people call Amdahl's law. And so I even wonder, did he really articulate it or not? But regardless, we call it Amdahl's law, and it's an astute and simple observation. And here's the observation. Suppose that 50% of your application is parallel and 50% is serial. Then you can't get more than a factor of 2 speed up no matter how many processors you run your app on. Okay, let's think about that. 50% parallel and 50% serial. Suppose the parallel part's miraculously executed in 0 time. Well, you still got to run the serial part, which takes half the original time. So the speed up, which is the ratio of the serial running time of the app to the running time of the parallelized app, okay, can't be more than 2, okay, because you've only made it go at most twice as fast, okay? And in general, okay, if a fraction alpha of an application must be run serially, the speed up can be at most alpha. 1 over alpha. So giving it a little thought, most people involved in computing can understand Amdahl's law, okay? Historically, Amdahl's law was used to argue that there's no point in making things run in parallel because most apps would have serial bottlenecks and you wouldn't be able to get much speed up for the hardware invested. It turns out they were wrong. There are many applications where the serial part is minuscule. Moreover, there are many apps for which you don't need to have the whole application run fast. So for example, maybe you're optimizing response time. You may only need to get a small piece of code to run fast to ensure that the user doesn't have to wait. And other situations involve time boxes, where you have a limited amount of time to do whatever you have to do. So for example, for real-time animation, such as are used in computer games, if you're a designer, you have a time box of about 16 milliseconds to render a visual frame at the rate of smooth motion, which is about 60 frames per second. Now, as a practical matter, the time box budget is really only about 13 milliseconds because you don't want performance variability outside your control to push you over the 16 millisecond limit, and there may be other overheads. So you leave yourself some wiggle room. So they tell the designers you've got 13 milliseconds. Okay. And so in addition, we found lots of huge things, machine learning applications and numerical computing applications and visual processing, et cetera, which have oodles and oodles of parallelism. Okay. So let's see how Amdahl's law can be used to quantify parallelism. So here we look at this, and we ask, he says, what fraction of the code must be executed serially? Okay, and it's just these 3 nodes. Okay, so Amdahl's law said that since the serial fraction is 3/18, which is 1/6, the speed up is upper bounded by 6. Okay, who guessed 6? Okay, I think we had one person guessing 6. Okay, yeah, so this is a pretty weak bound, okay? And for this trace, Amdahl's law doesn't give you much insight as to how much parallelism is actually there. Okay, it's a very weak bound. Okay. So now let's do some real theory and get to the point, okay? So it's important that you know Amdahl's law for cultural reasons. But the algorithmic theory in this area is so elegant and strong, it's a shame that more people don't know it. So I'm doing my part. I'm teaching it to you. Okay. So first, let's do some definitions. So let's define T sub P to be the execution time of the computation on P processors. Okay, so that's just very simple. Let's give that a name. Okay. There are 2 natural measures. Okay. The first is called the work, which is T1. T1 is the running time we get if we execute using just one processor. That's just adding up all the time of all the strands. So I execute nodes one by one, I measure how much time it takes, okay? And that is the work, okay? We know about work because the Bentley rules, for the most part, are all about reducing work. And we know the work of this trace. Okay, I just have to count up how many nodes there are. Okay, there are 18. Okay, because here we're assuming, once again, for simplicity, that each strand executes in unit time. Now, if they didn't execute in unit time, you can do the same thing. There's no big deal. Now, the second measure, I said there were two natural measures. The second natural measure is called span, okay, which is t sub infinity, also called the critical path length or computational depth in some papers. The span is the runtime if you had an infinite number of processors and there were no scheduling ahead. You're on an ideal machine, okay? Another way of looking at it is the span is the length of the longest path in the trace. Okay, so in this case, this is the longest path in the trace. Happens to be this one. Okay, and its length is 9. Okay, okay, and once again, you just add them up if they weren't all unit time. Okay, okay. Now, there are two important laws that we can derive from work and span. Now, I call them laws because Amdahl called his a law, or at least other people called his a law. I could call them a theorem or a lemma, but people will think that's too nerdy. Okay, so from a marketing point of view, we want to compete with Amdahl. I figure we should call them laws. Here's the first law. This law, as I mentioned before, assumes an ideal parallel machine, but the law actually does work pretty well in practice. The work law says that the time on P processors must be at least the time on one processor divided by P. Why is that so? So here's the idea. An ideal parallel computer with P processors can do at most P work per step. So suppose for the purpose of contradiction that T sub P is less than T1 over P. Then after executing for T sub P steps, the computer can't do more than P times T sub P work. But if T sub P is less than T1 over P, then P times T sub P is less than T1, so the computer can't have done all the work. Okay, you can look at this yourself, but the idea is that the assumption that TP is less than T1 over P has to be wrong because you would have done all the work by then. There's no more work to do, so you can't do too much. Okay. The span law says that the time on a finite number of processors is at least the time on an infinite number of processors. And in some sense, that's much simpler because you can always use a bigger machine to emulate a smaller machine, especially if they're ideal. Okay. So those are the two laws. Now, it's helpful to understand how to compose these things. And I'm going to skip over this, but you can take a look at this, at these slides. They're very helpful to look at. But I do want to talk about speed up. Okay, so T1 over TP, that's formally what we're calling the speed up. How much faster the P processor execution is than the T1 processor execution is. Now, we'd like T1 over TP to be P. Okay. If so, we have perfect linear speed up. We get P speed up on P processors. That's great. Okay, we're throwing P processors at it, we get P speed up. Okay. Linear speed up. Some people say perfect linear speed up. Okay. Now, usually we fall short and we don't get P speed up on P processors, and that's called sublinear speed up. Okay. And that's the second case. Okay. Now, the best possible outcome would be that we obtain superlinear speed up, okay? But that's not possible because the work law prevents you from getting it, okay? That's the unfortunate thing. You can't get it in this ideal model. Now, in practice, you sometimes get a little bit of, you can see occasionally a little bit of superlinear speed up. For example, when you run on more processors, you typically get more cache. So the total cache, the cache per processor may be the same, but you're getting more total cache. And that enhances locality and can result in superlinear speed up. But typically when you see superlinear speed up, you know, it's usually only a few percent. You don't see that too much. So finally, here's the definition of parallelism. The span law dictates that TP is greater than T infinity. So the maximum possible speed up given T1 and T infinity is, well, what's the largest that the smallest that TP could be. That TP could be. That's T infinity. That's the parallelism. So for this, another way of looking at it is the average amount of work per step along the span. Okay, and in this case, it's the work, 18, divided by the span is 9. Okay, and so the parallelism is 2 for everybody who guessed 2. Now, when I looked at this trace to begin with, I swear, I would have sworn there was more than a parallelism of 2, but there wasn't. Okay, here's fib again. Let's make our simplifying assumption, okay? What's the work here, okay? So that's pretty easy. We just add it up, okay, and we get 17, the 17 strands here. Okay, just ignore the activation frames, count the strands. What's the span? The span here is, well, let's take a slack pull. So let's do a quick slack pull if we can. Okay. 7 seems to be leading. Okay, turns out the answer is 8. Okay, it's a little bit, here's the path. Oops, let me see here. Let me do that again. So the path goes along here. Yeah, that's sneaky there, right? Oh yeah, most people just went down to the left and up. That's why they got 7. Okay. Okay, so, and the parallelism then is just the ratio, okay, which is 2 and 1/8. What that means is using many more than 2 processors can yield only marginal performance gains on this trace. Okay, of course, if n is large, fib has oodles of parallelism. Okay, now, silk scale. So, the OpenSilk compiler provides a scalability analyzer called Silk Scale, which is similar in some ways to Intel's SilkView tool. And like SilkSAN, it uses compiler instrumentation, and you don't have to eyeball this, okay, and figure out what it is, although you may have to do that on a quiz, okay? But you have to, but the idea here is that Silk Scale will compute the work and span for you. Okay, and it's really 3 tools in one. It has an analyzer, an auto benchmarker, and a visualizer. So here is, for example, a quicksort. Okay, and I think I'm not going to go through the details of quicksort here. And instead, so I had a thing, but because we got started a little bit late, I don't want to do it. But this is the kind of picture that it will give you. Okay, it plots the number of workers on the horizontal axis. And in the execution time plot, it's the runtime of the code, and in the speed up plot, it is the speed up. Okay. So, so here the purple dots, okay, are the measurements generated by auto benchmarking the code, running it on different numbers of processors. Okay, and Silk Scale will do that for you. Okay. And then let's focus on the speed up plot. That's where all the interesting stuff is, okay? So the analysis determines the work and span, okay, and it plots those. This is basically the linear speed up curve, which gives you the bound on from the work law. And this is the parallelism one. In this case, the parallelism is almost 20, okay, which is mediocre. We ran it, in this case, on I think it was 10 million numbers, okay? So it's 20. Usually you want about 10 times more parallelism than processors, but we'll talk about that next time. It also gives you this thing called burden parallelism, which tells whether the program might incur overhead. I'll let you look at this offline. I'll let you look at the work because I do want to cover the elements of the scheduling theory. Okay, so Silk allows the programmer to express potential parallelism in an application, and the scheduler maps the strands onto the processors dynamically at runtime. Now, it has a distributed schedule that's actually complicated, so we're going to explore the ideas with a simple centralized scheduler. And this is called greedy scheduling. And the idea of greedy scheduling is to do as much as possible on every step. Okay? So we're going to assume that we have an ideal parallel computer that incurs no scheduling overheads whatsoever. So let's look at a trace. Okay? So the scheduler is able to schedule a strand as soon as all its predecessors have executed. So suppose we've executed these guys. Then which things are ready to execute? Okay, it'll be these 5. Okay, those are ready. So let's say that we've executed the cerulean strands, or blue for all us programmers, okay? Which strands are now ready? Okay, and that's those. Okay, so we divide things into 2 types of steps. One we call a complete step, and the other we call an incomplete step. So here I'm illustrating with p equals 3 processors. And in a complete step, we have the situation that more than p strands are ready to go. So that's the case here. We've got 5 things ready to go and only 3. So what do? We just do as much as possible. So we schedule 3 of them. Which 3? Well, different schedulers make different choices. But for our purposes, it doesn't really matter, okay? We can run any p, okay? Complete steps are good because we're using all the processors. Okay, so let's say we pick those 3. Let's execute those. Okay. Ooh, that was actually a bad choice because we didn't make any new strands ready. Okay, because nothing more is ready than we had before. So now it turns out we have an incomplete step. Okay, there are fewer than p strands ready. And so what does the greedy scheduler do? It has no choice. It has to execute all of them. Okay? So we just run all of them. It doesn't matter which processors they run, but some processors will be idle, and that's inefficient. Okay? So let's hope that we don't have too many incomplete steps. Okay? And that's what the theory says. Okay? The theory says that any greedy scheduler achieves TP is less than or equal to T1 over P plus in T infinity. Okay? They do pretty well. Now, why is this an interesting formula? Well, if you look at the right-hand side, the first term is T1 over P, which is the work per processor. Well, that's the lower bound on TP given by the work law. And the second term on the right-hand side, T infinity, is the lower bound on TP given by the span law. The theorem says that the sum of these 2 lower bounds is an upper bound for greedy scheduling. That means, as we'll see in a moment, that greedy scheduling is within a factor of 2 of optimal. Now, there's a huge literature on scheduling theory, but if you want to know just one thing about scheduling theory, this theorem is it. Okay? So let's quick go through the proof, and you can look at this offline as well. Okay? Here's the proof. Let's just count up the complete and incomplete steps separately. How many complete steps can there be? Each step performs exactly P work. Okay? So the total number of complete steps, okay, can be at most T1 over P, because if it's done more than T1 work, because if there are more than T1 over P complete steps, it's done more than T1 work, and there isn't more than T1 work to do. So far, so good. There can't be that many complete steps because we'll run out of work. Okay. Now the incomplete steps, and this is the clever part of the proof, but it's also quite simple. The number of incomplete steps can be at most T infinity. So why? Let's look at the span of the unexecuted DAG. Okay? Each incomplete step is guaranteed to reduce the remaining span by 1. Okay, there we go. Okay, we reduced it by 1. Since there can't be more than t infinity times that the remaining span is reduced by 1, the number of incomplete steps can be at most t infinity, QED. Okay? As I mentioned, there's a corollary that the greedy scheduler achieves within a factor of 2 of optimal. Okay? But it turns out, I'll let you look at that, but here's the important corollary. Any greedy scheduler achieves near perfect linear speedup whenever the parallelism is much bigger than the number of processors. Okay? And the proof is, once again, fairly straightforward, but it does take some, these are simple proofs, but you got to get them in your head because they can be a little bit tricky to reason about. It's just algebra, but it can be tricky to reason about. Okay, so T1 over T infinity is much greater than P is equivalent to saying that T infinity is much less than T1 over P. So when I look at the greedy scheduling theorem, that's the sum of those two, and it's saying that the second term is much smaller than the first term. So this is really approximately T1 over P, and that's linear speedup. Okay, so we get linear speedup whenever that's greater, and we define the ratio of the parallelism to the number of processors to be the parallel slackness. How much more parallelism do you have than the number of processors you're running on? And a good rule of thumb is you want that to be like 10 or 20 or something. Okay. Now Silk's performance achieves something like this. It gets T1 over P plus order T infinity, and empirically you can use T1 over P plus T infinity as a good model. Okay. And it also gets near linear speedup as long as P is much less than T1 over T infinity. Silk scale lets you measure it. And so the takeaways are, to complete, the determinacy races are usually bugs, but they can be detected using silk-SAN and good regression testing methodology. The work and span laws provide lower bounds on parallelism, which is the maximum possible speedup. Silk scale can analyze the work, span, and parallelism of a computation. A greedy scheduler gives you linear speedup on computations with sufficient parallel slackness. So your goal is to create a lot of parallel slackness, although there's diminishing returns there. At some point, you got enough. And the Silk runtime system incorporates a randomized work-stealing scheduler that has strong theoretical bounds on its running time, like those for greedy scheduling. So the next two lectures are also going to be highly conceptual, so I recommend you take a look at some of what we've covered today. And I'd be happy to hang around and answer any questions, especially because I know I went a little fast through those latter slides. We got started a little bit late because I had technical difficulties. So thanks, everybody, and happy to chat for a few minutes if you want to enable everybody to chat.